Good evening, folks, and welcome to the Advent of Code C++ live stream. My name is Craig, and tonight we're going to be solving Day 11's Advent of Code puzzles in C++, or at least trying our very best to. Thank you for watching. If you are watching the live stream on Twitch, you can go to my channel description. You can find links to my YouTube channel where we have replays of all the past days' puzzles, and a link to my GitHub repository where I post all the code that we write in these sessions. If, on the other hand, you're watching later on YouTube, just check the video description right down there. You're going to find links to my Twitch channel for the live streams, and once again, my GitHub repo where we write all of the code. So, tonight, day 11. Recently, the puzzles have been getting a little trickier, a little more algorithmically interesting. A lot of fun. I think, it's not strictly a linear scale of difficulty as we go through Advent of Code, and it's kind of subjective anyway. I know that in previous years, I have sometimes gotten tripped up by not remembering my modular arithmetic all that well and needing to look up some stuff to figure out problems. So that has been those kind of puzzles have been stumpers for me. I know different things are difficult for different people, but we're going to do our best. And if I get stumped, might have to take a step away and think about it for a little more and come back to the problem. But we'll see how we do. So for tonight's puzzles, I have our typical setup here of just a bare bones C++ program. Doesn't do anything, just returns 0 to the calling environment. I've included my check library for assertions and my IO library to read puzzle input, because we use those pretty much every day. And I've set up a build target for this part 1 solution in the Bazel build system that we're using. And I've already got a command here, to run the program, and it's been built and runs here and does nothing as we expect right now. So now we're just waiting for the puzzle to drop. Should come out in about a minute and a half. Go ahead and look at my personal stats here. So it's only part 2 on day 6 was the only time we came in under 1,000. But, we're not trying to go at absolute breakneck speed in these streams. We're trying to, I'm talking out loud. I'm trying to, explain my solutions as I'm going through them so that hopefully you get an idea of my thought process as I'm working through these. But that being said, it's still nice to finish relatively quickly relative to the world. So yeah, we'll see how it goes. I was looking on Eric Wastel's Twitter account the other day. He is the person who designs all these wonderful puzzles for us and runs Advent of Code. Apparently now more than 500,000 people have gotten at least 1 star on some Advent of Code puzzle across all the years that it has been running. So this is a big deal. A lot of people, coming together to work on these puzzles for fun during the holiday season. And we are about to work on one right now. Dumbo Octopus. Here are a large cabin full of rare bioluminescent Dumbo Octopuses. They seem to not like the Christmas lights on your submarine, so you turn them off for now. There are 100 octopuses arranged neatly in a 10 by 10 grid. Each octopus slowly gains energy over time and flashes brightly for a moment when its energy is full. Though your lights are off, maybe you could navigate through the cave without disturbing the octopuses if you could predict when the flashes of light will happen. Okay, each octopus has an energy level. Your submarine can remotely measure the energy level of each octopus. Your puzzle input. So you have a 10 by 10 grid of 100 octopuses. Very neatly arranged. Energy level of each octopus is valued between 0 and 9. Here, top left octopus has an energy level of 5. Bottom right one, energy level 6, so on. You model the energy levels and flashes of light in steps. During a single step, the following occurs. Okay, so this is kind of a cellular automaton, it seems like. Energy of each level of octopus increases by 1. Any octopus with a level greater than 9 flashes. This increases the level of all adjacent octopuses by 1, including diagonally adjacent. If the splash causes an octopus to have an energy level greater than 9, it also flashes. This process continues as long as new octopuses keep having their energy level increase beyond 9. An octopus can flash at most once per step. Finally, any octopus that flashed during the step has its energy level set to 0, as it used all of its energy for the flash. Okay. Adjacent flashes can cause an octopus to flash on a step, even if it begins that step with very little energy. Okay. Octopus is highlighted when it flashed during a given step. Okay. Yeah, so we see we're highlighted there. Okay, see how these steps go. After step 10, there have been a total of 204 flashes. Many more configurations. After 100 steps, there have been a total of 1656 flashes. Okay, how many total flashes are there after 100 steps of input? So we will save our link as day11.txt. Now, this grid of numbers from 0 to 9, or possibly going above 9 when we get to the point where something flashes, reminds me a lot of something that we saw in a previous day for the volcanic vents. Now, I'm going to try and remember which day that was. That wasn't day... Was that day 7? No. Was that day 6? Which, no. One of these previous days, this grid here. So, yeah, I don't know if that's actually going to be that useful to copy, come to think of it. What did day 9 look like? What was that? Oh, yeah, height map. That looked like quite a lot like it. I think I am going to copy and cannibalize this height map class, and we'll get rid of a lot of it, but just like the parsing logic is already there, so we might as well reuse it, right? So again, we'll put all our stuff in this anonymous namespace here. Go ahead and paste that in. So instead of calling it height map, we'll call it octomap for the octopuses. Octopi instead of heights. Octopi. Total risk, and so these things are, just related to that other day's work, so we're not going to really talk about those. But now for adjacent cells, it's actually going to be up to 8 cells that are adjacent to a given cell because we're counting diagonally. So let's go ahead and... No, that's... Yeah. So we'll go ahead and put in some includes for the things that we're actually using here, like abcell container inlined vector.h. Get that inline vector. So there's going to be 8 adjacent cells for a given coordinate for a given area. So we'll say 8 there. Basically, anywhere where it references heights, it's going to actually be octopi. Oh, so this is assuming a square grid, but actually it should... yeah. I mean, this is a square grid anyway, so it doesn't really matter. So we've already got something that returns the 4 cardinal directions here. So the next thing that we need to do is just combine like the X and Y parts of it. So I'm going to break these up a little bit. So these are, the horizontals. These are the verticals. And actually, maybe we'll just name some of these conditions, like just to make this a little easier. So we'll say, so left means that there are cells to the left. Coords dot first is greater than 0. Right means that there are cells to the right. And we can do similar things for up and down. Up, cell above. So you use this coords dot second condition here. Oh, that should be const bool up. Const bool down. We will use this. Okay. And now it's basically if, I guess we'll start at the left and maybe we'll go around clockwise. So we'll say if left, that, if left and up, then cells dot and place back coords dot first minus 1 coords dot second minus 1. If just up, then it's going to be this one that we already previously wrote. It's going to have the same x coordinate, and it's going to have the y coordinate minus 1. If right and up, because again, I'm just going around this clockwise to do this. We'll say cells dot and place back coords dot first plus 1 coords dot second minus 1. If just right, we just increase that x coordinate and do nothing with the y coordinate. If right and down, it's going to be like right and up, except that we increase the y coordinate instead of decrease it. If down, we just increase the y coordinate, keep the x coordinate the same. And finally, if left and down, then we decrease the x coordinate and we increase the y coordinate. Then we just return those cells. So that's, and then this is low point and basin size. We are not going to keep because they're only really relevant to the previous problem. And we should include vector for vector and utility for pair. Those are things that we use there. Let's go ahead and do our basic I/O here. We'll just say standard vector of strings can be the lines. We'll use that pre-written I/O routine, read lines from file with the first argument to the program. And then we'll say octomap. We'll construct an octomap from that list of lines. And so now we need to actually write the step function for this cellular automata where we simulate the flashing of the octopi. So let's go ahead and say in step, and the integer that it's going to return is the number of flashes that occurred in the step. So first thing we do is for, I mean, I know it's a 10 by 10 grid, but I'm going to make it based on the actual size of the array, size of the map, just in case. Make it a little more flexible than it necessarily needs to be. So for x coordinates and range, for y coordinates and range, first thing we're going to do is just octopi x, y. We're going to increment that energy level. So energy, so if the, actually, we're going to keep a set of octopi that flashed, I think. Maybe we can do this in stages, but yeah, I'm gonna want to use we'll call these flashers. So we'll say if increasing that led to the energy level going above 9, then we're going to emplace those coordinates in the set of flashers. So first thing we do, increase everybody's energy level by 1. Now we have this list of flashers, and then for let's see here. So for each one of these flashers, if it flashes, we want it to increase the energy level of all the adjacent octopi as well. So we'll say I guess this is really small. We don't necessarily need to do it as a reference. But we'll say for the adjacent cells next to a flasher, you know what? I actually kind of, I think that maybe I want to do this as a queue instead of as a set. Because, and we'll only count an octopus as flashing when it first hits an energy level greater than 9. When it first hits 10, we'll put it in the list of flashers, because I think then we can just keep going on the queue until it's empty. So we'll say a queue of coords called pending flashers, and then we will put stuff on pending flashers if incrementing it gives us exactly 10. So then we will say, while pending flashers is not empty, we will take the first element from that queue, and then we will apply basically the same logic to so then all of its adjacent cells, we're going to increase their energy. Octopus can flash at most once per step. Yeah, okay. Cool. So for the adjacent ones next to the flasher, we are going to increase their energy level and if it hits 10 for the first time, then that adjacent one is going to go on the list of pending flashers. So we do this until there's no more. Now, I think, if I remember correctly, we actually need to count the number of flashes. So we'll say each iteration of this loop is a flash. And then the final thing that we need to do, well, eventually we're going to return total flashes here, but the final thing that we need to do is go through the entire thing again, and any cell that flashed, we should reset the energy level to 0. So if its energy level is greater than 9, we're going to reset it to 0. We could also keep track of all of them that flashed, but this is a 10 by 10 grid. Like, it's going to be fast either way. I don't think that it really matters, like optimizing for sparse versus dense levels of flashiness. So, okay, so we've got our step function, and now to get the whole solution, we just can say simulate for a certain number of steps. So again, we have total flashes 0 for step 0. Could have made that const, I guess. But for that number of steps, we will run our step function and add the number of flashes from that step to the total flashes, then return the total number of flashes. So finally here, in the main function, we will output the result, the total number of flashes after 100 steps. So I believe that's everything that we need for this. We just need to add the include for the abcell inline container, or inline vector container that we're using. Okay, let's go ahead and try running that. on our input for day 11. It says we have 1,732 flashes from our field of octopi. Let's see if that is correct. Boom! All right, that's part 1. Seems like the individual flashes aren't bright enough to navigate. However, you might have a better option. The flashes seem to be synchronizing. Example above, the first time all octopuses flash simultaneously is step 195. Okay. If you can calculate the exact moment when the octopuses will all flash simultaneously, you should be able to navigate through the cavern. What was the first step during which all octopuses flash? Okay. So this is easy enough. I'm actually going to just keep doing it in the same program here. Not even going to, do the basic commit, but we just need to run the simulation until we get a step where there are 100, where all 100 octopuses flash. Yeah. Okay. I wonder if this is going to be like an off by 1 thing here, but we'll see. Yeah, that's honestly all we have to do for this part is just we're going to keep on running this loop until this function returns 100, indicating that all the octopi flashed, and then we will know which step we were on. Although if I'm looking at the counting here, sorry, just it's going to say before any. Okay, so we have the value before any steps. That's nothing, but yeah, I think we're good on this. But if it happens to give us a wrong answer, I'm going to try other things. Let's go ahead and run it on our input. 289 steps is the answer that we get. Let's see if that is correct. All right. That's not correct. I strongly suspect off by 1 on this. So what I'm going to do is I'm going to take the original puzzle, the test input here, before any steps, and see, if we need to adjust our counting, basically. So we'll use that, use our same program on test.txt. It says 194. So we need to count that first step, I guess. Huh. All right. Well, let's do that on our test input. Off by 1, so they'll get you every time. So 290 is the answer that we should be wanting. Oh, I'm sorry, I didn't show this over here, but I basically just started from 1 instead of 0 to resolve that off by 1. Put in 290. Okay, there we go. Let's see how we did today. All right, pretty good. Below 1,500 both steps. I think we got there maybe a little bit faster by kind of reusing some of the code for a previous day to handle this grid and, build up, these adjacent things here. I don't think we ever actually used this energy at method. You can probably delete it, get rid of it there, and still we'll be fine. Because we just directly access the grid of octopi in all cases. But yeah. This was not that difficult. It's a cellular automaton. I think, last year there were several puzzles that used some version of the Game of Life, which is another, which Conway's Game of Life, which is another, kind of famous cellular automaton. But basically, it's one of these things where you can take a step function in time and the state of all of the cells in this grid is dependent on what the state of everything was in the previous one after you apply some rules. And that's what we get with our octopus grid here. So maybe we will be seeing these octopi again in future days of puzzles. But at any rate, I want to thank you all for watching, for going through this puzzle with me. Again, if you are watching the live stream on Twitch, you can check my channel profile. There you'll find links to my YouTube channel, where we post replays of these streams, and my GitHub repo, where we upload all the code. If, on the other hand, you're watching on YouTube, just check the video description right down there. You're going to find links to my Twitch channel and that same GitHub repo. Thank you again for watching. I hope you had fun with me tonight, and I will see you again for Day 12's puzzles tomorrow night. Bye-bye, everyone.